Hello, this is Mr. Henry, and welcome to Lesson 4.6, Constant Rates. This question says, how do I use graphs to represent proportional relationships? And the warm-up asks, what do you think the graph of a proportional relationship looks like? Actually, we talked about this a little bit in the last lesson, if you remember. But put down your thoughts. What do you think it might look like? Maybe make a sketch or so if you have an idea. I'm not going to answer it yet. I'm not going to go through it because we'll go through it in the lesson. I just want you to think about it first. Get some ideas down. So a constant rate, just like before, is a situation where a variable is moving uniform with respect to time. It never moves faster or slower. It always goes at the same pace. So somebody bakes at the same pace. Somebody's running constantly at the same pace. Typing a paper, whatever the situation is, building houses. They're always doing it at the same speed. They don't move faster. They don't move slower. It's like a machine. They're designed to go at a certain pace all the time. And that's what a constant rate is. So our first example here asks, it says, Tonya is driving at 46 miles per hour. We want to know how many miles Tonya can drive in t hours. Write an equation to model the situation. Okay, so step one is we want to write an equation. So we know she can drive 46 miles per hour. So already I'm thinking we got miles and we got hours. So we've got 46 miles in 1 hour. And the other part is, well, just make up some imaginary number. How many miles, m, we're going to use, can she drive in t hours? The m and the t are proportionally related. So miles and hours here, miles and hours here. If we cross multiply and solve for m, so we want to know how many miles, that will give us our little equation that models this situation. It will show us the relationship between the number of hours and the number of miles. So let's do that. We get 46t equals 1m, and we're solving for m. We're getting the m by itself, so we're actually done. We don't need to divide by 1. I mean, you could, but it doesn't do anything. So m equals 46t. So for every 1t, for every hour, you're going 46 miles. So this is a relationship we're going to use. And we're going to take this and eventually turn this into a graph. So first step, you want to write your equation. Step 2, we're going to fill in a little table. So our equation, m equals 46t, right? 46, yeah. So to make this little equation, all we're going to do is I threw my equation in here and make up some time. So if you go like 1 hour. So if your time is 1, 46 times by 1 gives you your miles, which is 46. If you go 2, 46 times by 2 is 92 miles. And 3, you just kind of continue the same process. 46 times by 3. We're filling out a table that's going to basically give us our graph. 46 times by 3, that one I'm a little sketchier on in my head. Here we go. 46 times 3, 138. And 4 and 5. M equals 46 times by 4. M equals 46 times by 5. All right, let's see. 46 times by 4. Clear. 46 times 4 equals 184. And then clear. 46 times by 5 equals 230. All right, so we have a table of values. This is our x. This is our y. So when we're doing our graphing, you can actually think of this like some ordered pairs. 1, 46, 2, 92. And our graph is going to be exactly this, 1, 38. So we're going to take our graph, which is actually on my next page, you have it on your paper, and we're going to make our scales, and we're going to graph these points, and we're going to see what shape it makes for us. So my x coordinate goes up to 5. My y scale needs to go up to about 230. All right, so let's see here. I've got this graph space. So my x is going up to 5. Let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So if I make that 0, 1, 2, 3, 4, 5. See? And my y-axis is going up to about 230. Let's see. Well, counting by 1s and 2s and 5s is probably not so good. 10s, maybe, I don't know. 0, 10, 20, 30, 40, 50, 60, 70, 80, 90, 100. If this is 100, 230 is going to be too big. So 10s is no good. Maybe 20s? 20, 40, 60, 80, 100. 20, 40, 60, 80, 200. 20, 40. That would put 230 like right here. That's not too bad. So let's do that. So what's this? This was 20, 40, 60, 80, and we get the idea from there. So that's 200, 220, 240, 260, 280, 300. All right. Now it's going to involve me flipping back and forth the page quite a bit, but you have all your numbers there. So what we're going to do is we're just going to graph. So that first point was what? 146. So 146. Well, there's 40, so 46 is just a little bit above. Okay. 292. 2, there's 80. 90 would be halfway, so 92 is just a teensy bit above. And we've got 3, 138. Let's see, there's 20, there's 140. So 3, 138 is going to be probably about there, just really close to the 140. And we have 4, 184, and 5, 230. So 4, 184, and 5, 230. That way I just don't have to keep looking back from page to page. All right, so 4, 184. 4, this is 180 here. So 184 is just a little above. And 5, 230. 5, 200. There's 240. 230 is halfway right there. Now, when we did this graph, we only picked certain values. In fact, these are not even the values I picked on my answer key. I used 2, 4, 6, 8, 10. It doesn't matter what values you pick. What you should notice is our graph should look very similar, though. And even if we picked decimal numbers, if I picked 1.5, 1.5, I can bet you is going to be like in here. Probably 75 something. I don't know, let's see. If m equals 46 times by 1.5. 46 times by 1.5 equals 69. Is that about 69? Yeah, that's right about 70. And even if I pick something in here like 1.25, I would expect 1.25 would be that ballpark, which is maybe 55. 46 times by 1.25. I'm thinking it's going to be about 65. I'm sorry, 55. 57.5. Okay, so this graph, even if you pick numbers that are not 1, 2, 3, 4, 5, it should still follow along this line. You can pick any numbers in between here, and you notice what shape this is making. And actually, this will be a nice, solid line. My line is terrible. I recommend you using a book or something, or if you have a straight edge, I'm going to use a line tool. There we go. And that, is clear. That line is perfectly straight. Now, my dots are not going to be perfect, obviously. So, but that shows you the relationship between the amount of time and the distance that this car traveled going 46 miles per hour. Every 1 hour, 46 miles. And it just keeps going up at the same rate. Example B. Same idea. It says Rose can type 1 page in 4.5 minutes. Graph this relationship. Now, I didn't give as many steps this time, taking some of the supports away. So what we did before is we came up with an equation that modeled the situation. That allowed us to plug some numbers in. So we need to come up with an equation. So we have pages and minutes. Page, minutes. So 1 page in 4.5 minutes, and that number of pages in that number of minutes. Cross multiply these things out gives us 1 minute equals 4.5 pages. This is our little equation that represents the scenario. So I'm going to throw him in there. Minutes equals 4.5 pages. Actually, I have this not quite the way I want it, because if I'm going to try to find the number of pages here, I want this to be P equals. So that's an easy fix. All I have to do is take my equation over here and solve for P. So if I divide by 4.5, divide by 4.5, these cancel. P equals 1 over 4.5m. A little bit uglier, but it's the same process. P equals, and you can even have m over 4.5. Just it's a division. That's what this is. All right, so let's make up some time. So I'm going to use 2, 4, 6, 8, 10 in this case. Just random numbers. If you don't like 2, 4, 6, 8, 10, you can use 1, 3, 5, 7. You can use, they don't even have to be in a pattern. Like here I'm counting by 2s. You can even say like 2, 3, 5, 12, 15 if you want. Just making up some other numbers. It doesn't matter what you pick, decimals, fractions. The relationship is still true, and so the graph would still be the same. But to make my life easy, I'm going to stick with these numbers here. So, number of pages, 2 over 4.5. Number of pages would be 4 over 4.5. I'm plugging the number of minutes into my equation for the number of minutes. And I'll go through and do my calculating after this. 8 over 4.5. And 10 over 4.5. Okay, calculator time. So, 2 divided by 4.5 equals 0.44. So if you work for 2 minutes, you should have almost half a page. And what about 4? 4 divided by 4.5, 0.88. I think I see a pattern. 6 divided by 4.5 is going to be 1.33. And then 8 divided by 4.5, 1.77. And finally, 10 divided by 4.5 equals 2.22. Now, those aren't the easiest things in the world to graph, but they're not terribly hard either. And also, as I was saying before, you can choose any numbers. On my answer key, I just took a peek-see at it. I use the numbers 5, 10, 15, 20, 25, kind of my bigger numbers. But we're going to get the exact same graph either way. So my graph space is a little bit smaller here. I remember my x-axis, I counted up to 5, so I'm going to do again 0, 1, 2, no. I went up to 10 because I did 2, 4, 6, 8, 10. 2, 4, 6, 8, 10. And my number of minutes, or number of pages, went up to 2.2. So I need some sort of scale. This is my pages. This is time. Let's see. Well, 1, 2 would be bad because 2.2 would only be this tall, so I have all this wasted space. So skip a space 0.5. I'm planning. Skip a space 1, skip a space 1.5, skip a space 2, skip a space 2.5. That looks pretty good because 2.2 would be right about here. So I'm counting by 0.25, like a quarter, 50 cents, 75 cents, $1, $1.25, $1.50, $1.75, $2. So that's what I'm counting by. I'm counting by 0.25. That seemed to work out pretty well. It filled up most of the space on my y-axis. So that's what I'm going to use. I wanted this 0.5 in there. Okay, so my little table here gives me the points 2, 0.44. So if you type for 2 minutes, 0.44. So this is 0.25, 0.44, I don't know, around that ballpark someplace. We're not going to get exact. 4, 0.88. 4, 0.88. Well, there's 1. There's 0.75. It's going to be a little bit closer to 1. I'm going to call it over here someplace. 6, 1.3. 6, there's 1. There's 1.25, 1.3. Probably there, roughly. 8, 1.77. 8, there's 1, 1.25, 1.5. This is 1.75. I'm going for 1.77, so just a teensy, itsy, bitsy bit above that. And finally, 10, 2.22. 10 to 2.25, so 2.22 is just a little bit below. Now again, you can clearly look at that and go, yeah, that is a line. If I would take my line tool, hopefully, look at that, it goes through all my dots. So my graphs, my dots are pretty darn close. Maybe not exact. If you use different numbers, you're going to get same or different points, but along that same diagonal, that same line. So if I used 1, if I plugged in 1, was it 4 point? It was m over 4.5. If I plugged in 1 here, 1 divided by 4.5 equals 0.22. So 1, 0.22, that's 2.5. 2.2 is a little bit lower. That still matches with our line. And any points along the line would give us the same thing. So, in the previous two examples, what shape did the graphed points make? And what conclusions can you draw about proportional relationships? Go ahead and answer the question. Alright, so you should have seen in the previous two examples, the graph made a line. A straight line here, straight line here. So the graphs of proportional relationships are linear. Linear means it makes a line. And the second part says, what conclusions can you draw about proportional relationships? Well, proportional relationships are linear. They make a straight line. The graph of any equation, in fact, any equation that we've seen this whole module, the graph of any of them would be a line. I mean, it might be this way, or flat. None of them have been up and down. But they're all lines. You're not going to find one of these equations, if you graphed it, it's not going to be some squiggly. Okay? They're all straight linear equations. Letter C. Emily paints at a constant rate. She can paint 32 square feet in 5 minutes. What area, A, can she paint in T minutes? Okay, so first thing we need is we need our little equation, and since we want this eventually to be A equals, that's just going to help me out later on. So she can paint, we got amount she can paint in minutes. So paint in minutes. Now, the variables that they have here in their table are T and A. So the minutes is time and the paint is area. So you can paint 32 in 5 minutes. And how much area in T minutes? Cross multiply gives us 32T equals 5A. And since we want the A by itself, we're going to divide by 5. Those cancel, and area equals, well, 32 divided by 5, whatever that is, 6.4 T. So this is the equation that shows the relationship between the time and the area. Every 1 unit of time, so every minute, she can paint 6.4 units of the area. So area equals 6.4 time. Every unit of time, she can paint 6.4 more feet. All right. So let's do, I don't know, 5, 10, 15, 20, 25. Why not? I'm just making some numbers up. And so in each equation, A equals 6.4 times by 5. Ooh, I know that one. Let's do it over here. It's going to be 32. Area equals 6.4 times by 10. That's going to be 64. Area equals 6.4 times by 15. I could do it in my head, but I don't want to. 6.4 times by 15, 96. Area equals 6.4 times by 20. It's could probably be like 128. And area equals 6.4 times by 25. And I don't know. 6.4 times by 25 equals 160. So now we have our table of values with our x and y coordinates. This is the x and this is the y when we're doing our graphing. And so we make our table. So my scale in the x is up to 25. My scale in the y is up to 160. So up to 25. There's 10 lines. Counting by 2s won't work. Counting by 5s, 5, 10, 15, 20, that'll work. 5, 10, 15, 20, 25. There's 0, 0. And then I wanted to go up to, what was it, 130, 180, 160. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So 10s won't work, but anything slightly bigger than 10 probably will. How about 15s? Skip a space 30, skip a space 60, skip a space 90, skip a space 120, skip a space 150, which make this 165. That's right? 160? Yeah, that worked for me. So I'm counting by 15s each line. I'm just labeling every other just so it's not cramped with numbers. And so now we can graph. 5, 32. 5, 32. 10, 64. 10, 64. 15, 96. 1596. 2128. 2128. And 25,160. 25,150, 160 would be halfway right there. And just to show that they are in a line, look at that. It's perfect. So that is a straight line. And same thing as before. This equation shows the relationship between the two variables. Every unit of time gives this much unit in area. And that's actually a major topic in here, is understanding that if you go 1 unit this way, you go up, what was it, 6.4. So every 1 unit is 6.4 more here. 6.4. If I go 2 units, it'll be another 6.4 up, and all of those little 6.4s add together to give us this line. Okay, and so it is actually a line that cuts through this diagonal and would fill in every number between. So we just picked the 5, 10, 15, 20, but if we picked 12.3, well, 12.3 would be like right here. It'd probably be right around 45. Just because I'm curious, what was the formula? Area equals 6.4t, and if I said 12.3, 6.4, and we said that should give us probably around, what do we say, 12.3 was right about 45. Let's see. 6.4 times by 12.3, please, 45? What happened? Oh, I'm stupid. That's not 12.3. That's like, well, this would be 7.5, so 7.3. How about that? 6.4 times by 7 point, I messed up. 6.4 times by 7.3, 45? Yeah, so that's really darn close to 45, so that's pretty good for me. Okay, so that just helps you see that relationship between the amount of time and the amount of paint, or the area, P-A-I-N-T, the painted area. Alright, here is letter D. If you could please pause the video, try it on your own. When you're ready to continue, hit play, and we'll go through it together. Alright, so let's see what we got. Hopefully you started by finding your linear equation. So the relationship between the time and the minutes, or the time in miles, I should say, would be, let's see, time miles it says he can walk 1/2 mile in 6 minutes. So the amount of time is 6 minutes. The distance is half a mile, 0.5. And then time and minutes, and we cross multiply, giving us 6m equals 0.5t. We would like this solved for m, so we have an m equals, makes it easier to find our m values. So if I divide by 6, m equals 0.5 over 6t, which seems a little ugly, but it's not that bad. So m equals 0.5 over 6t. I guess the values I'm going to use for my amount of time, I'm just going to go 0, 30, 60, 90, 120. I like actually plugging in 0. I didn't do it in any of the previous problems, but plugging in 0 is actually really easy because m and 0.5 over 6 times by 0, it's always going to give you a 0. Anything times by 0 is 0. So in all the previous problems, I could have had a 0 in here, and 0, if you plug it in, gives you 0. And when I did my graph, you can kind of see, when I made my line, I always had it going through the origin, through the 0, 0, just because I know that's how it works out, and I guess I didn't really mention it, but the line does go through the origin because it makes sense. If Emily painted for 0 minutes, she got 0 painted. If Joseph walked for 0 minutes, he went 0 miles. He didn't go anywhere. So that makes sense. I just never did it in any of my previous problems. M equals 0.5 over 6 times by 30. Let's see here. 0.5 divided by 6. What is that? Ugly number. All right. Times by 30 gives us 2.5. Okie dokie. Clear, clear. Oops. M equals 0.5 over 6 times by 60. And my guess it's just going to keep going up by 2.5. So I bet I'm going to get 5. 0.5 times by, oopsie, no, divide by 6 times by 60 is 5. And since I kind of went in a pattern this way, this will also be a pattern. So 7.5 and 10. 0.5 over 6 is 90. M equals 0.5 over 6 times by 120. And there we go. So my x values on my graph, my x values have to go up to 120. My y values have to go up to 10. So now I know what my scale is going to look like. My x values have to go up to 120. My y values have to go up to 10. And if I remember right, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Perfect. I'm just going to count by ones. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And this guy's up to 120. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I could count by something funky like 12s. I mean, it's not terribly bad, I guess. But when I'm on my scale here, I was going by 30s. I mean, 30, 60, 90, 120. So I'd like to go something similar to that. So can I do 30, 60, 90, 120, 150? 60, 90, 120, 150. I mean, that only takes me here, but that's still most of the space. That's time. It was this guy. This was miles. All right. So let's graph this thing. 0, 0. Got it. Oh, missed it. 0, 0. He's easy. 30, 2.5. So if you walked for 30 minutes, he's 2, 3, 2.5 is here. 60, I remember, it goes up by 2.5. So 60 would be 5. 90 was 7.5. Or 7, 8, 7.5 is halfway between. 120 was 10. 10. And we can see again that this makes a line. If I use my line tool, there we go. Goes right through all of them. Nice perfect straight line every time. And just as before, if I would pick values that weren't just 30, 60, 90, if I pick in between numbers, it would still fall along this line because the relationship was, what was it? Miles equals 0.5 over 6t. So for every minute, every 1 unit here, they went that far, which was like 0.083 or something. 0.5 divided by 6. Yeah, 0.083 miles. So every minute they walked 0.83 miles, and all those little 0.83 miles add up over time to give you this line. In the summary box it says, what have you learned about proportions and their graphs? Go ahead, pause the video right now, answer the question. When you're ready to continue, hit play, and we will go through it together. And my answer is the graphs of proportions are linear. That means they always form a straight line, which is true. And we've seen it from all of our examples. Doesn't matter what numbers you pick, you always get this nice straight line for your graph. This has been lesson 4.6. Thank you for watching.